So now we move on to a slightly more complex case, and now we're looking at our spectrum of isopropyl. I think this is in the liquid, the little picture of an infrared spectrometer up here, and like most spectrometers now, they're all computerized, so you can generate a transmitting spectrum, or you can generate an absorbent spectrum, or just by computer manipulation. But so that's something that it looked like. And here we have our more complex molecule, this time propanol, but this is the liquid state of propanol. And of course you work out the number of theoretically predicted vibrational modes, and you have 30. But you can see now the spectrum is a bit it's less nice than the nice spectrum we had for formaldehyde. It's quite broad, some of the bands, and clearly there's not altogether there's not 30 bands there. So this is more typical of what you'd observe in the liquid state. So you put this into your into your spectrometer. What you'd like to do is you'd like to be able to assign the bands in some way. And I suppose from what we know already, we'd say, well, this high energy region here must be associated with some kind of stretching vibrations or stretching modes, whereas down here these are probably the bending modes. So again, you can do that, and people well, assigning this spectrum, this band here, the highest energy band, is due to the OH stretch. So you've got an OH group here in the alcohol, and you can see it's a very broad band, and that's characteristic again of when you have this in liquid state, you have the propanol molecule, a little hydrogen bond with another propanol molecule, so that will affect the broadness, if you like, of the band. So that's another thing you have to consider when you're looking at something like a liquid state spectrum. And then people, using various methods, can assign these bands here, so to CH3, because you use CH3 group, and then someone assigned this band here to a CC stretch mode, and then as you can see down here, we have some assignments to bending modes, CH2 bending, and backbone, what they call backbone stretches. This region here is usually not that well defined. We'll talk about it in a minute. It's called the fingerprint region. You get a lot of bands, and it's almost impossible to assign them, but it'll be the same for the molecule. So sometimes, if you have an unknown and you run this infrared spectrum, if you look in this region here, you can sometimes just compare it with, say, a library of spectra. You can identify the molecule fairly easily. Right, so let's move on. So again, this is a liquid state spectrum, so as you can see, it gets a bit messier down the gas phase, but of course this is what we're more interested in. So we have to deal with that. And again, the spectra of larger molecules can be very difficult because you can't assign all the theoretically predicted modes. So here we have a lactic acid, which you should know about. This builds up in your muscles when you haven't got enough oxygen to break it down all the way to carbon dioxide. And this is the infrared spectrum of this molecule. So you have CH3, CH, OH, C double bond O, OH. And again, you can see it's a very broad and rather complex looking spectrum. But again, you can, using analysis of where you expect these bands to occur, you can predict. We've already seen that the OH stretch, so you should get the idea. We had the OH stretch before, hydrogen bonded OH stretch before in the alcohol, and we saw it occurred around here, around the 3000 wave number region. So even if you didn't know, much about infrared, from what we know already, is you'd assign that to the OH stretch. And we also saw in the propanol molecule that the CH3, we call CH3 stretching, the hydrogens in the CH3 group here, their stretches occur also around this region. So that's a CH3 stretch, and then we'll come on to it later. The C double bond O stretch characteristically occurs here about between 1500 and 1700. And and it's usually quite a strong infrared band, and that occurs there. So you'd say that's due to the presence. If you didn't know what this molecule was, you'd say there's a C double bond O bond there as well. And then you have this region here, which is hard to assign, but this is due to the bending modes. And again, it's called a fingerprint region because it'll be similar for all molecules of this type. Right, okay. Yeah, okay, so what I've done here is right, let's just move it on. Yeah. So as I say here, what you classify this region here is the fingerprint region. So this would be characteristic of this molecule, and it's undefined bending modes for the backbone of the molecule. Whereas this region here is what we call the functional group region. So here you can work out, well, there's an OH group present, or there's a CH group present, and especially there's a carbonyl group present in the molecule. So again, so this is a fingerprint region, so you have this area complex overlap, and it's impossible to assign, so it can act, but it's useful because it can act as a fingerprint for that molecule. Okay, so this is probably just emphasizing again, functional group region 4000 to 1200, fingerprint region 1200 to 400. Again, it's all in centimeters minus 1. Takes more energy, we've mentioned that. So stretching bands are found usually in the functional group region, and the bends are typically in the fingerprint region below 1200 centimeters minus 1 to about 400 centimeters minus 1. So this is the type of analysis an infrared spectroscopist has to go through in general. This is kind of a general, if you're looking at, you have your molecule, you run the infrared spectrum, and you want to know what's the structure of it, say. You look for these functional groups first, and then you might look in the fingerprint region. Does the fingerprint region, these will be stored in a library, does it match with any molecule that is known? And of course, all spectroscopies, like we're talking about spectroscopies in general, an organic chemist or a biological chemist would go through a range of spectroscopies. So you'd do an infrared analysis, and this would give you some information. But you'd also perhaps run the UV spectrum, and that would give you more information. And then you'd run something like we're going to talk about NMR. You'd run the NMR spectrum. So usually an analysis of a molecule is a combination of all different types of spectroscopies, and that combination then will give you much more and more structural and electronic information about the molecule. So there are the general principles of assigning infrared spectra. And again, you can get more specific, and as we'll go on in a minute, there's books and tables written on where you expect different modes to occur. So here we have the infrared region going from 4000 down to about 400 or 500 centimeters to the minus 1. And here what we've done is we divided it, or I haven't done it, but this has been divided into different regions. And this again is to help you assign. So here the 4000 to about 2500, you expect to see OH, NH, or CH stretches. So if you see these bands, excuse me, in your infrared spectrum, then you can work out that you perhaps have these groups present. And some other analysis might tell you, an elemental analysis might tell you, well, you haven't got an OH group, oxygen or nitrogen in the molecule, but you have carbon, so you'd know then it's CH, wouldn't you? So then this region here, I don't know where it's got to, 2,500 to 2,000, you expect to see triple bonds, like C triple bond C and C triple bond N. And then you have, say, this now the region here, 2,000 down to about 1,750. You have not many infrared bands present in many molecules. And then you have an important region here. You've got the double bond, C double bond O, C double bond N, C double bond C. Especially C double bond O, it gives a very strong, intense band. We haven't talked about the intensity sometimes, but Certain bands like C double bond though will give a very intense band. So if it's very intense, you can almost certainly, around this region, you can almost say right away it's a C double bond O stretch. And then you have, as we talked about here, this is a fingerprint region. So usually it's some kind of bending mode that's going on in that region. And as we say here in the bottom, people have done a lot of work on this. There's extensive tables and charts to aid you in assigning the IR spectral regions. And as brought down here is more an art or an experienced spectroscopist than actually, I suppose, a rigorous scientific method. So here's just some examples. So you can see here they have classified, this is for organic biological molecules, and they've classified the different types of groups you can have. And here you then have in this column here, you have where they come up, in what region of the spectrum. And also, as I said, we didn't mention the intensity, but the intensity sometimes can be a guide. And you can see here you describe a band as weak, medium, or strong. So you can see they have different characteristics in the intensity as well. So this again is what you would use. So you can see here there's books written on this type of analysis. And again, here's another example here of classifying different types of functional groups.